Good day, everyone, and welcome to today's webinar with CWNP. My name is Tom Carpenter. I'm the CTO at CWNP, and today we're going to be talking about LoRaWAN. And we'll not only talk about LoRaWAN, we'll also talk about LoRa, the PHY protocol that is actually used with LoRaWAN devices. Now, as we get into this, we're going to be talking about IoT very briefly, just to define the context of the use of LoRa devices and LoRaWAN networks, and then we'll get into some of the architectural components in a LoRaWAN deployment, and specifically into the data rates, modulation, how everything works in order to make a LoRa connection function. And you'll understand when we go through that some of the use cases and applications of LoRa and LoRaWAN. Now, I will warn you, I grew up in West Virginia, so I tend to say LoRa as Laura, more like the woman's name, so I will just warn you that my pronunciation may be a little unusual. But we'll all know we're talking about the long-range IoT protocol. Of course, as always, we are on Twitter at CWNP and at Carpenter Tom. And this webinar will be recorded and provided on the YouTube channel. So if you want to view any past webinars or other recordings we've released, you can go to YouTube, search for CWNP TV, all one word, CWNP TV, and you'll find the channel where you can subscribe to be notified when videos are posted. So maybe you miss a webinar, you'll always be able to catch the recording after the fact and so forth. We do have some exciting webinars coming up this year. Later on in the year, we're going to be talking about the new version of CWDP and CWAP, as well as the new CWIDP that's coming out, and CWISE, which will be released this year. And we'll also be talking about some other interesting things. In August, we have an exciting webinar planned where I had came across a very old document related to ciphers and encryption processes from the 1700s. It was written in older French and, frankly, had not been translated into English in any way that I could find. And so I sought out an individual, Manon Lassar, who is a CWNE actually, and asked if she would be willing to translate the document for me. And she did that. And myself and her and Phil Morgan will be releasing a paper detailing not only that original document written in the 1700s and the implications it still has for encryption today, but also we'll be talking about encryption in general and the importance of it in our wireless and IoT networks and so forth. So that's going to be an exciting one. And we're also going to be talking later on in the year about 802.11ax and the real world. What is being implemented? What's not being implemented? That is part of the standard, and what are the real-world implications of 802.11ax. So some exciting things coming up later on in the year, and with that, we'll go ahead and get started with today's topic, the LoRaWAN Deep Dive. Now, first of all, we'll define the Internet of Things. I've defined this before in other webinars and in other contexts, so I won't take a whole lot of time on this, but the general concept of the Internet of Things is that anything can connect from any place at any time to the internet and then transfer information. Now, that's the general thinking behind the Internet of Things. But I want to be more specific, and I've chosen these definitions, and I use them all throughout our IoT track materials. So that would be CWISA, all the way up through to the professional level certs, CWIDP, CWIIP, and CWICP. The ITU definition is that IoT is a global infrastructure for the information society, enabling advanced services by interconnecting physical and virtual things based on existing and evolving interoperable information and communication technologies. Now, you'll notice the ITU definition doesn't even mention the word internet. It has something close, interoperable information, but not internet. And that word, interoperable, has nothing to do with the internet. This is saying that these devices can communicate information in such a way that other devices or components can understand it because it's in a standard format, interoperable information. Think things like JSON data, for example. Also, some people prefer to call it JSON. But whether you call it this or that, it's the JavaScript object notation language, and it's used to define data, right? It's a data structure language. And basically, they include that, but they only have the other interword here, interconnecting. So how are they interconnecting? Well, the DHS definition is that it's the connection of systems and devices with primarily physical purposes, for example, sensing, heating, cooling, lighting, motor actuation, transportation, to information networks, and then they say parenthetically, including the internet, via interoperable protocols often built into embedded systems. Now, there's a reason that I've chosen these, and that is that even though the word internet is in the acronym Internet of Things, the reality is that many devices that are sold as IoT devices literally are implemented and never connect to the internet. That is to say that they use local communications of some type of protocol, whether it be a wired protocol or wireless, and they communicate with a gateway or a coordinator or a controller, depending on what the protocol calls it. And then that device sends it to some local server on the local network where it's processed, and it never goes to the internet. And yet we're implementing IoT technologies. So the concept of IoT really should not be constrained at this stage in its evolution to only things that connect to the internet. Although one of the great advantages of IoT devices is potentially using internet technologies, cloud services, for example, through Azure and Google Cloud and AWS and many others, to process that IoT data in a streaming manner or in some other manner that provides instant value or the proper value that we need out of that data. The whole point of sensing things is to do something with your senses, right? The reason why we can see is so we can do something in relation to what we see. The reason we smell is so we can do something in relation to what we smell, and so forth. And in the same way, there's no reason to have a sensor on a toaster if we're not going to do something based on what is sensed, right? And so therefore, an IoT device that is sensing and gathering information, or that could possibly be an actuator and take some action, either way, there needs to be something done with the data or some data that drives actuation, that causes us to do something to or through that IoT device. And so in many cases, we do utilize the internet. We do go to the cloud and take advantage of cloud services for these kinds of things, but it doesn't have to be that way. And that's why I chose these definitions, because IoT can simply be what you might call internetwork of things instead of Internet of Things. And you could also just refer to it as the lowercase I internet, right? Because early on, before internet came to mean this worldwide network of interconnected routers and systems, the word internet simply was short for internetwork, basically devices that network with each other. All right, so now we need to talk a bit about a topology as we get into LoRaWAN here. There's a topology called star of stars. And basically, a star of star topology implements a local star that communicates with at least one, but maybe multiple remote stars. LoRaWAN is actually defined in the LoRaWAN specifications as a star of stars topology. So the local LoRa device communicates with the LoRaWAN gateway, and that's the first star. There might be multiple local LoRa devices that are communicating with that LoRaWAN gateway. And then it forwards the message to a network server where multiple gateways could forward it from the LoRa end device to the same network server. So we could have multiple stars connected to this one network server. And then the network server could be connected to other networks as well and have yet more stars or more star networks introduced in that way. For example, you might have 10 sensors connected through a gateway and 10 actuators connected through another gateway. And the network server takes the data that's coming in from the sensors, passes it off to a third network where that data is processed, and then that third network sends a command through the network server to the actuator network to actually take some action. Now, no, it doesn't have to be that way. You could have the actuators and sensors working through the same gateway, but I'm just giving you an illustration of how it might end up becoming a star of stars type of network topology. So this is important to keep in mind. This is the general topology defined in the LoRaWAN specification for how LoRaWAN works. Now, before I go any further though, I've used a couple of phrases here and I want to make sure you understand them. I've mentioned LoRa and LoRaWAN. These are not the same thing. A LoRaWAN is the actual network architecture or structure overall. And it includes your network server. It may include join servers and things like that. And it also includes the end devices and the LoRaWAN gateways that are all involved in the communication. So it's the whole big picture of the network. LoRa devices are devices that communicate with the LoRa protocol, the physical layer protocol, which is now today owned by Semtech. It's a proprietary protocol. So you basically just get devices that have the LoRa chip on them, and then they can communicate using LoRa modulation. The LoRa modulation is not publicly known, but if you're interested in it, you can do some digging around on YouTube. There have been some great presentations by people who have reverse engineered the modulation to be able to understand how it works, even though Semtech has kept it secret. So you can think of it kind of like people going into the kitchen and they keep trying different recipes until they find the one that tastes just like a particular restaurant's recipe. Well, in the same way, people have reverse engineered this modulation so that they can understand it. So you can get that information. I'm not going to go to that level of depth today, but know that LoRa refers to that local link between a sensor or an actuator or another type of IoT device and the LoRaWAN gateway. That's where the LoRa protocol is used. The LoRa protocol is not typically used between the gateway and then the internet or the rest of your network. That's going to be Ethernet. It's going to be 4G, 5G. It's going to be even maybe Wi-Fi. It's going to be something else, right? That is that back-end communication behind the gateway. The LoRa protocol is used specifically on that local link. So it's important to understand the difference between those two terms. So if I say LoRa, and I try to be scientific as best as I can in use of this terminology, if I say LoRa, I'm referring to that local link modulation protocol. If I say LoRaWAN, then I'm talking about the whole network that includes everything from the end devices through to the network servers that are involved in the whole process. Now, LoRa, the name, means long range. Simply LoRa, short for long range. So it's a long range protocol. So what's the difference? What makes a long range versus a short range protocol? Well, range is a function of several things: the frequency used, channel bandwidth, transmit power, antenna gain at both the transmitter and the receiver, receive sensitivity at the receiver, modulation, coding. All of these things impact the range, the distance at which we can receive and properly process a signal. Okay. So you know about these things if you've studied Wi-Fi, right? You already understand that you have longer range with 2.4 gigahertz than with 5 gigahertz due to the aperture of the antennas, due to the design limitations of 5 gigahertz antennas, and that even though the signal has propagated there, we can't pick it up as easily with the antennas that we manufacture. And you may also know that your range gets even farther when you go below 2.4 gigahertz and you go down to 900 megahertz or 800 megahertz or 400 megahertz and so forth. And so lower frequency generally gives you longer range, but also optimal antennas become longer and longer. Now you can still use shorter antennas, but the optimal antenna is longer the lower the frequency is. And then you can get by with shorter antennas the higher the frequency is for optimal antennas, because it has to do with the wavelength, right? The antenna design is related to the wavelength, which of course is driven by the frequency. All of that is interrelated. So range is a function of the frequency, first of all, whereas lower frequencies can generally be received at greater distances or ranges. And then there's the channel bandwidth. How wide of a block or chunk of frequency am I using? The wider the channel, the shorter the range, generally speaking. Then there's the transmit power. The more output power I have, the greater distance I can receive it at. Now, for health reasons, as well as interference and cooperative reasons, there are limits on the output power based on regulations around the world in different regulatory domains. So we can't just keep turning up the power to get a longer and longer link. We might like to, but we can't do that for, first of all, regulatory reasons, because the regulatory bounds are well below any kind of health risks. So there's the regulatory reason, but then eventually you would get to a health concern if you went with transmit power too high. Obviously, you could go on nearly to infinity until your transmit power was at the level of the radiation power of the sun, right? And that's not good. Antenna gain is transmit and receive. So at both the transmitter and the receiver, we can have antenna gain. And it's not uncommon to have more antenna gain on the LoRaWAN gateway than you have on the end devices. And that does help us with reception and communications. And one of the reasons for that is the end devices are often these little devices. We want them to fit in little spaces. We don't want them to take up too much space. And they may have a PCB-based antenna or something like that, or they may have an external antenna, but it's much smaller. So the antenna on the end device is usually, not always, especially in outdoor agriculture and things like that, but for indoor deployments, most certainly, we tend to see shorter antennas on end devices, longer antennas on gateways. The receive sensitivity is a factor. This has to do with the radio module as a whole. It has to do with its filters that are used inside of the radio, the amplifier, all of these. So you want low noise amplifiers, for example, and components that are used in building the receiver so that it has the best receive sensitivity possible. And then the modulation impacts it. The more complex a modulation, the better signal to noise ratio or signal to interference and noise ratio that we need. And so with less complex modulation, we can get by with lower SNR, even negative SNRs, as I'm going to talk to you about a little bit later on. And so modulation impacts the range. And then coding, because particularly with forward error correction, things like that, we have the ability to literally fix problems in the received communication because of the coding. And so that helps us to get better range still. So all of these things can impact the actual range at which we can communicate. So what are these ranges? Well, let's talk about it a little bit. I have the two low power wide area networking protocols that are commonly used outside of cellular. So I'm not talking about NB-IoT or LTE-M or anything like that. We're talking here about LoRaWAN and Sigfox. And compare that with the other protocols we see here. So 802.15.4 can get up close to the expected ranges of LoRaWAN and Sigfox, up to 10,000 meters, but that's extremely rare that an 802.15.4 link works at that distance, but it is theoretically possible. Most of these others, you can see they're far less than that, 2,000 meters and less. And that's at the far end of the range, okay? Wi-Fi is not usually used for a 2,000 meter range, although you can create Wi-Fi links at, say, 11 megabits per second. It's been done at over 100 miles. And so it is possible, but it's not practical because when that link was created in Utah, in Nevada, it was actually created using huge satellite dishes, great big giant antennas. And so it's not practical for most Wi-Fi implementations to think you're going to get that kind of range. Most of the protocols, as you can see, that are commonly used in IoT are really designed for in-building type solutions or a mesh solution where every 100 to 300 meters we have another mesh device. Whereas LoRaWAN, you can see, up to 15,000 meters. And that's the farther end, theoretically speaking, but there's some great videos on YouTube of people pushing the boundaries. And so one person has a YouTube video on the world record for a LoRa link. And it's pretty long, and it shows you. And by the way, he built it with simple microcomputer boards that you can just buy and run the LoRa modulation on them, either with a built-in chip or with an add-on module to get LoRa capabilities. And so he didn't have any kind of fancy stuff that he custom engineered to make it happen. And he was able to create a very long distance link. So certainly you have greater distance here. This is one of the key benefits of LoRaWAN and Sigfox, is greater range in communications. Certainly easily into the thousands of meters, even though most people are not worried about 10,000 plus meters. 1,000, 1,500, 2,000 meters, things like that are not at all uncommon. And we're even seeing further advancements to well beyond 15,000 meters in certain special case scenarios now. So very interesting things with LoRaWAN, and it definitely does have a long range. So again, LoRa is long range, and it's a low power wide area network. And the modulation uses sub 1 gigahertz. So it's 900 megahertz, 800 megahertz, 400 megahertz, and so forth. It's down below 1 gigahertz. LoRaWAN is the protocol standard defining the higher layers. So think the Mac frame formats that are actually passed as modulated LoRa communications, the network layer, all of that is dealt with, okay? You need a LoRaWAN gateway because we're not really dealing with IP addressing from the end device to the gateway. So if you want to get it from that gateway to somewhere else on an IP network, the gateway is needed to accomplish that because it knows how to talk IP and the end devices don't know how to talk IP. So here is an example then of the LoRaWAN topology. So we see our end devices and we see our gateways, and then we have a network server, which may or may not be a combo network server and join server. So you can have a network server separate from the join server, or they can be one physical device that plays both roles, but there's still a logical different component or role within the server. The join server is what lets the LoRa devices that do over-the-air activation get onto the network. The network server is what then allows communications to happen ongoingly. And then your application servers, well, they're just the servers that take this data that's coming in from the end devices and process that data. Or they make decisions to send commands to actuators to take some kind of an action. Now, do note one thing here in this image is that the physical layer does not have to use the LoRa modulation. It can use frequency shift keying, and there's even a frequency hopping algorithm that's supported in some regulatory domains. And so you don't have to always use LoRa modulation, but that is the modulation that is the big driver that makes people want to use LoRaWAN solutions in most cases. We do use 128-bit AES encryption from the end device all the way through to the application server. So that application layer payload is encrypted there. And then we also have AES 128-bit encryption at the network layer as well. So 2 layers of encryption using 2 different keys in the communication process. So this gives you an idea of the LoRaWAN topology overall and the things involved. But before I leave this slide, let me point out that there are really 2 ways that you can use LoRaWAN. One is you can implement your own entire architecture. So you can have your own gateways that talk to your own network server and that in turn talk to your own application servers. Or you can use a service provider. Probably the most well-known is called the Things Network. That network is a LoRaWAN network, right? And there are many others as well. So if they have local gateways to you, you can just have your end devices communicate with those gateways, and then they'll go through their cloud network and then out to your application servers. There are people that also do provide cloud services, so you can run your applications in their cloud and use the LoRaWAN technology. So there's several ways that it can be done. Where do you get gateways? Well, you can buy pre-built gateways. There are some manufacturers that create LoRaWAN gateways that are designed to be part of the Things network, so you can easily get them on the Things network, and it's free to add a gateway. The Things network wants you to add a gateway, but you have to allow other people to get through your gateway onto their network as well. You can also go through other organizations that have LoRaWAN architectures built out for you, and they'll provide you a gateway, and you plug that gateway into your network, and it is automatically authorized, synced up to your cloud account, and then you can get all the data from your end devices out of your cloud account. So there are a lot of different ways that this is done, but there is another way. If you build your own architecture, you can literally build a LoRaWAN gateway with a Raspberry Pi. It doesn't have to be a super advanced device to accomplish the goal of a gateway, because all the gateway has to do is speak the LoRa modulation protocol for the local link and have an interface to be able to speak IP to get out to the rest of the world and translate between them, communicating from the end devices to the network and the join server. And then the network server is what allows communications with the application server. And so you can build a gateway using things as simple as Raspberry Pi solutions. So the LoRaWAN protocol architecture, realize that the application layer sitting at the top is what provides really the LoRaWAN functionality. Do not confuse this with the OSI model application layer. Okay, this is the LoRaWAN application layer. And LoRaWAN is defined well. So all the stuff at the LoRa MAC and up is defined very, very well. The LoRa modulation is what is kept private and has been reverse engineered by some to understand how it works, but it's that proprietary technology that Semtech provides through their chipsets. And the key thing then to understand is that the actual application layer is well defined. You can go to the LoRa Alliance, and from there you can download documentation on everything about how the application layer functions. You'll also see that the LoRa MAC has 3 classes of devices, A, B, and C. I'll talk about them in a little more detail in a couple of moments. And then at the bottom here, you can see just some of the regional bands that are used. So EU can use 868 or 433, depending on where you are. US uses the 915, and so forth. Now, I call these the 800, 400, and 900 megahertz bands, just to simplify it. But the specific frequency bands are 868, 433, 915, 430, and so forth. There is a document that I'll talk more about later that you can read, freely available to you, that explains the different channels and data rates and spreading factors, which is a unique feature of LoRa that are supported in the different regulatory domains. So what are these 3 classes of end devices? Class A, B, and C. Well, the simplified view is that Class A gives you the greatest battery life, but the highest latency in downlink communications. That is to say, when you need to get a message to a Class A end device, it's going to take longer to get it to it than it will to get it to a Class B, or it'll be longer for Class B than it will for Class C. Okay? And that's because of the way they listen for downlink communications. But because they listen differently, this also does impact their battery life. So Class A devices, longest battery life, greatest latency in downlink communications. Class C, shortest battery life, lowest latency in downlink communications. Class A devices do support bidirectional communication, uplink and downlink. But the way it works is different for each one of these. So I'll talk about that a little bit more later on. LoRaWAN gateways are kind of like an access point in a Wi-Fi network for the end devices, only of course they're for the LoRa communications. It receives signals from the end devices and demodulates them and then sends them to the network server through the backhaul, as I've said. The gateway provides a lot of telemetry type information specifically related to the RF environment, though, that is very useful for the network to know about in relation to these devices. So it not just sends the payload for the communication from the IoT device to the network, but it also says, oh, and when I received this payload, here's the signal strength I saw. Here's the signal noise ratio. This was the time of arrival. Here's the channel they sent it to me on, and this was the data rate they used to send it to me. So all of that extra information is sent to the network server, and it allows for management of the end device if needed. For example, the network server might indicate to that end device, you need to do an adaptive data rate and increase the data rate or decrease the data rate accordingly. So that kind of thing can be accomplished because of this extra information that is sent up to the network server. The frequency bands, I'm not going to read these to you. If you watch this on YouTube, you can pause it here and look through them. But here you see the different regions and the band and the frequencies used. Again, if you look into the document that gives you this regulatory information, it's the document is called LoRaWAN Regional Parameters. So if you just go to Google, search for LoRaWAN Regional Parameters, you'll find this document, and that middle column, EU 433, CN 470, if you just search the document for that, it'll take you right to the section that details how the frequency band is used, what is the channelization, how wide are the channels, what's the spacing between channels, all of that. So that information is available to you in their documentation. How do we know what the transmit power is? Well, the maximum EIRP is 36 dBm. That's the maximum that could possibly be transmitted anywhere in the world, right? But that's not allowed everywhere in the world. There is a command, LoRa communications use something called MAC commands. MAC commands are commands that are used in relation to configuration and communication about the status of the network. And so the one called TX param setup request sets the maximum power. And inside of that particular communication, there is a subfield called max EIRP. And it's going to have a coded value that is 0, 1, 2, 3, 4, and so forth through 15. So from 0 to 15, 16 different possible values. It's using 4 bits to accomplish it. So it's bits 0, 1, 2, and 3 in this communication, in this MAC command. So 0 translates to 8 dBm, 1 to 10, 2 to 12, 3 to 13, and so forth. That's what this translation table is telling you. So basically, the lowest EIRP is 8 dBm. The highest is 36 dBm. So that kind of translates for you what that actually is. Now, the regulatory domain may constrain what that actual output power is going to be. And it is important to know that in addition to transmit power constraints, some regulatory domains constrain the time on the channel, how long you're allowed to communicate. So for example, in the European Union, the devices have to use a duty cycle of 1% or less. But in North America, it's not percentage based, but each time they're on the channel, they have to be on the channel for 400 milliseconds or less. So there are constraints in different regulatory domains that vary. And that's why when you get a LoRa device that's pre-manufactured, you've got to make sure you're buying one that supports your regulatory domain so that it can comply with these requirements. So in the EU, it's going to make sure it doesn't communicate more than 1% of the duty cycle. Now, you might think, well, 1%, that's not very much. Well, no, but realize that's each device, right? So if the device is using all of that 1%, and I have 100 devices, I'm using 100%, aren't I? Okay, so it's not as limiting as it sounds at first. Even if you look at the average Wi-Fi network, you will see that a lot of your clients, if you look at the average, not necessarily the least well-behaving client, But if you look at the average client is probably using less than 1 or 2% of the actual duty cycle, of the time that it could be using on the channel. And so it sounds very restrictive, but it's not quite as restrictive as it might sound in the first place. Now here we have the LoRa channel widths and spacing. So this information is also available in the LoRaWAN regional parameters document that I've mentioned to you. This is just an example from the North American 915 megahertz ISM band. It varies by each region, and they use completely different frequency bands, and they may use different channel widths and so forth. So for example, we have channel widths of 125, 250, and 500 kilohertz. Well, what we can see is that when we're dealing with the North American 915 megahertz band, we're working with 125 kilohertz channels or 500 kilohertz channels, but we don't have 250 kilohertz channels. Okay. It's also important to note that in the North American 915 megahertz band, that the channel spacing is different, which makes sense. The channel width is narrower, and so we can have narrower channel spacing, right? 125 kilohertz has 200 kilohertz of channel spacing. 500 kilohertz has 600 kilohertz of channel spacing in the downlink, and 1.6 megahertz or 1600 kilohertz channel spacing in the uplink. And so the channel spacing is different depending on whether it's uplink or downlink. It is important to know that the channel bandwidth does end up impacting the data rate. So let's take a look at that and you'll see what I mean. So here we have an example from data rates for Europe, and we'll look at one of the US here in a moment. But you can see the lowest LoRa modulation data rate is represented here with 250 bits per second. Notice that's not kilobits per second. That's literally 250 bits per second. We don't get up to kilobits per second until SF9 data rate 3, which is technically the fourth data rate, right? 1.7 kilobits per second. And notice the highest LoRa modulation here for Europe is a 250 kilohertz wide channel with a spreading factor of 7, SF7, giving us what they call data rate 6, and that's 11 kilobits per second. So this protocol, at this moment, you may have had your first exposure to the reality of IoT protocols. This protocol is not intended for, streaming video or what we use Wi-Fi for, right? One of the reasons why the range is so long, so great for this protocol is because we're not using super high data rates. We're not using super high bandwidth, and we're not using super high data rates. And because of that, we can get longer range. The longest range, of course, is going to be at that 125 kilohertz channel, SF12 at only 250 bits per second. But think about it. If I have a temperature sensor, how many bits does it take to say what the temperature is? I could say what the temperature is in 8 bits or less in most cases, depending on the level of accuracy I want. If I want a very high level of accuracy, maybe I go up to 16 bits, right? So I don't need a lot of bits to get that information through. And then, of course, I have my Mac frame overhead information and all the rest of that. But I could report my temperature once every 30 seconds or once every minute, and I could do that okay with 250 bits per second. Wouldn't be a problem. So you can see then that for a lot of these sensors, a lot of these IoT type devices, it's not really driven by needing high data rates. It's needing stability and possibly range and long battery life. Because I might want this LoRa device running on SF12 to last on the battery for 4 or 5 years without having to go out and replace the battery. Sigfox, a protocol that competes with LoRa but has very big restrictions in the amount of communications a day, 140 communications per day by default. That protocol promises 10 years of battery life out of your sensor. And so obviously it depends on the sensor, depends on what you're doing with it. But the point is that it's not about massive data rates. It's about reliable communications over the distance or the range required. So here we're looking at where that information you just saw on the slide came from. So remember, I have mentioned to you this LoRaWAN Regional Parameters document. Well, these are some images I captured from that document, just so you could get an idea of what it looks like. And again, you can freely download the document and look through it. So here we're seeing the EU 863 to 870 band, and you can see that it tells you a bit about how it works. Now, I'm not going to read all of this to you. I just wanted to expose you to what the document actually looks like and the kind of information that's shared. And so you can see this detailed information in table format and so forth, and you can see the lowest data rates as well. Now, I do want to point out, I had mentioned earlier that LoRaWAN can support long-range frequency hopping spread spectrum. And you see it right here. That is an uplink only modulation. So the gateways will never use that modulation to communicate to the end devices, but the end devices can use it to communicate with the gateway. So just so you know that difference is there. And if you are preparing for, say, the CWICP exam, we do not test on LRFHSS on the exam. Our focus is on LoRa and FSK because those are predominantly the modulation methods that are used worldwide. And so we can see then the document details, definitely worth taking a look at. So let's take a very quick look at another example. This is the modulation, encoding, and data rates for North America, again coming out of that same document that's available to you for free. And you can see we're using 125 kilohertz and 500 kilohertz channels. And with that bandwidth, I should say, rather than channels, with that bandwidth, you can see that I can get a data rate as high as 5.5 kilobits per second for 125 kilohertz or 12.5 kilobits per second at 500 kilohertz. On the downlink, it's all 500 kilohertz. So downlink is all 500 kilohertz. And let me explain why that is. At first, you might think, well, why would I want that? We don't use it very often. Well, most of your LoRa gateways, while they're talking, they can't be listening. And so the way LoRa works, it's kind of an aloha type network, which just means I'm going to start talking when I want to talk. And the gateway needs to be able to hear that. And a gateway could potentially listen on 8 different channels at the same time. So what does that mean and why do I care? Well, what it means is that the system must address the reality that we want to be talking, the gateway wants to be talking as little time as possible, right? So we want to default to, whenever possible, using higher data rates in order to accomplish that. So that's one of the big driving factors there in using the wider channels to get the highest possible data rate whenever we can. So this is just an example of the functions within North America. Now, one of the things that came up in both of these, we looked at an example of Europe, we looked at an example of North America. You can go through the document, you can see China, you can see all the rest of the world. There's this thing that keeps coming up, spreading factor. So I want to talk to you about what in the world is spreading factor, because that's one of the most confusing parts to people that come from Wi-Fi to IoT and particularly LoRa modulation. So spreading factor, here's a graphical representation of it, and then I'm actually going to show you a spectrum capture so you can see it there as well. So the green is SF7, the red is SF8, and the blue is SF9. So look at the amount of time, but notice we're not using any more frequency. So we've still got the same frequency bandwidth, 125 kilohertz or what have you, right? We've got the same frequency bandwidth, but we're taking more time with SF9 to spread across the frequency than we are with SF8 or SF7. So going back, notice that SF7 has a higher data rate than SF8, which has a higher data rate than SF9, and so forth. So why is that? Because we can chirp faster. So LoRa uses something called a chirp. This is a modulation method that was invented all the way back in the 1940s. So it's nothing new, but using it for the type of data we're using it for here is relatively new in nature, especially in a widespread deployment model. So basically, what we're dealing with here is faster or slower chirps. And here you see it in a spectrum capture. So you can see what this looks like, and very similar to the graphical representation that we saw before. You can think of this, there's a good reason this is called a chirp. If you think about a bird and how it might chirp, you can hear a bird making a chirping noise that's drawn out, or you can hear very, very fast successive chirps that mean something, and people that study them understand it much better than I do. But here, what we're dealing with is the fact that we can have up chirps and down chirps. And that is to say we can be going from low frequency to high frequency or high frequency to low frequency. And that can mean different things. Okay, so for example, the preamble, which as you may know from your study of other wireless communications, is the start of the communication, right? The preamble can actually have 8 downward chirps and then 2 upward chirps. And now we'll start talking. So I'm giving that as an example. So we've got downward chirps in sequence and then 2 upward chirps. And now we know, okay, it's time to start the actual data that's being communicated. Now, the thing is then that this wider the spreading factor, the lower the data rate, but the higher the resiliency. And that's why as we have a wider spreading factor or a higher spreading factor, because it's really not wider, it's spread over time. So a longer spreading factor is the word I should be using there. The higher value or longer spreading factor gives us more resiliency because it's slower, right? It's a good way to think of it. It's slower. And if you imagine someone speaking in another language that you're just getting started learning, it's much easier for you to understand everything they say if they speak more slowly. However, if you know the language well, it's also very frustrating for you for them to speak that slow because you could be receiving it at a higher rate, right? Well, that's analogous to the concept here. So if I'm at a very great distance, I might need it to be a slow spreading factor so that I can process it better at the receiver. But if I'm at a closer range or I have little to no interference, then I might be able to do a faster spreading faster and narrower in the time scale. Okay. So let's see that. So here, this is where things get really cool, right? We can literally, with SF12, receive a signal as weak as minus 137 dBm. That is 20 dB into the noise floor. I want you to think about that if you've studied Wi-Fi, okay? Because if you study Wi-Fi, you know you're always looking for a positive SNR, aren't you? You're looking for, the signal is 3 dB greater than the noise, or 6 dB, or 12 dB greater than the noise. But the signal is always greater than the noise to some level. That's what you're looking for, right? But here, we can have the signal buried in the noise, and we can still get it out. That's how resilient that this very low data rate chirping modulation actually is for those communications. And one of the reasons why we have such a significant range available to us. And you can see then with SF12, the target is 14 kilometers, though people have gone greater distances than that, down to SF7, 2 kilometers, giving us the highest data rates. Now, there are lower spreading factors as well, okay, but I'm just talking about the ones that are commonly used and available in most regulatory domains. All right, so let's talk a little bit now about these Class A, B, and C operations. I mentioned that Class A gives you the longest battery life. Well, the reason for that is a Class A device sleeps potentially for minutes, hours, days. It sleeps until it needs to talk. And then when it needs to talk, it wakes up and communicates and then it'll stay awake to listen for incoming communications. Now, I'm not going to go into extensive details about this algorithm at this point in time. It is documented in our CWICP study guide, which was released last year. It is also documented in the LoRaWAN specifications. So there are multiple sources of that. But the big thing I want you to know is a Class A device sleeps until it's ready to talk. And then after it's done talking, it will listen to see if the network has anything to say to it. And if it doesn't hear anything after the first period of listening, it will wait one more period. And if it still doesn't hear anything, it says, all right, I'm going back to sleep. I'm tired. And that's Class A, all right? Class B, on the other hand, says, well, we're going to sleep, but wake up for beacons. All right, so it's considered a beacon mode device, Class B. Easy to remember, Class B, beacon mode. That's not why it's called Class B. It's just arbitrarily Class B because they're A, B, and C. But it's a beacon mode device. And basically, it gives you regularly scheduled opportunities for an end device to receive downlink communications. So the downlink message is called a ping. Don't confuse this with the ping command that uses ICMP to test our IP networks. That's not what this is. The downlink message is just called a ping in the LoRaWAN specification. And that message is sent at this regular interval so the device can receive it. So it has to wake up regularly. Automatically, you now know, since it can still sleep, but it has to wake up regularly, its battery life is not going to be as long as Class A. However, a Class B still does Class A stuff. That is, if it wakes up and has something to transmit, then it's going to listen to see if the network has anything to say back before it goes back to sleep and then goes back to the regular interval of waking up to see if there's information for it. Finally, we have Class C operation. Basically, instead of sleeping after the uplink, it opens a window immediately. So going back, notice that with Class A, we go to sleep for a moment, then we wake up, then we sleep, then we wake up. With Class B, we do the same thing after an uplink, but with Class C, we just immediately listen, and then we also still have the Class A window, and then we simply listen forever. Okay, so in other words, we're going to keep right on listening. We're never going to sleep. So a Class C device is always there. When would I use it? When you have a device that you need to be always there to receive a communication from the network. Maybe it's an actuator, for example, and you want it to receive a message quickly if you want it to turn something on or turn something off or something like that. And so that's a Class C operation device. Now, let's talk a little bit about getting these devices on the network as we get close to wrapping up all these things we're talking about how LoRa and LoRaWAN work. There are two methods of activating your end devices, the actual IoT end devices. One is over-the-air activation, OTAA, and the other is activation by personalization, ABP. Over-the-air, device manufacturers can generate provisioning parameters, and secure keys can be renewed on a regular basis. Devices can also store what you might think of as logical identities that can dynamically and securely switch networks during its lifetime. So it doesn't have to be locked into a particular network. It can be moved. It is considered by most to be the more secure method over the air. So they basically use a join procedure, which I'll talk about here in a moment, in order to synchronize with the network server. And they use the join server to accomplish that end goal. And they then become part of the network. Activation by personalization is simpler. I get in the hardware and just turn it on my network and it works, right? But they're personalized at fabrication. So when the manufacturer is building them, all of the device IDs and keys are preloaded on them so that you don't have to go through the join procedure. But they are tied to a specific network. Now that network they're tied to, not necessarily your physical network, but the things network or some other network, right? And so LoRaWAN network providers may give you the option to get devices from them that are already pre-activated with this activation by personalization so that they can get on the network without your intervention. Okay. So the end device activation for over the air looks like this. The end device talks to the network server by sending a join request to it. And then the network server finds the join server and it forwards that join request to the join server. It then responds with a join answer to the network server. And assuming that answer is an approval, then the network server sends a join accept to the end device. And then the end device sends a data packet to the network server. And the network server sends the data packet to the application server. And once all of that has happened and we know that we have full communications through the network, we get our app key from the application server, which is used for communications of all information on an ongoing basis. Okay. And so this is where your network key is created earlier. It's created by step 5. But your app key is created once you have active communications with the application server in the general architecture. Again, this can all depend on pre-provisioning and other actions that could take out-of-band provisioning and so forth. So some people have done some creative things with this, but this is the general process, the one defined in the actual LoRaWAN specification. All right, so what do we use this technology for that we've been talking about? Well, here you go. Okay, I grabbed this from a list of just one vendor who sells a bunch of sensors and things like that that are LoRa sensors. And they say it can be used for COVID-19 support, smart agriculture, smart homes, smart industrial, smart water metering, smart metering of other things, smart cities, smart environments. Well, okay, in any one of these environments that are listed here, I think you can imagine some scenarios where you might have an IoT device that needs high data rate, something that needs maybe 50 to 100 to 200 kilobits per second or something. And you just can't get that with LoRa. So it's not the solution for that. But in all of these different industries or verticals, I'm sure you can also think of things that only need a few bits per second and they'll be okay. And so that's the big key. What is the data rate requirement? What is the battery life requirement or power consumption requirement? What is the range requirement? And when you can answer those 3 questions, the data rate, the power, whether that's battery life or power consumption, and the range, you'll know whether something like LoRaWAN or something like Zigbee or Bluetooth or wireless HART or something else is the better solution. So the key thing is to understand what the protocol offers and then determine your needs from there. All right, that's the scheduled content we had to deliver today, so I'd like to thank you for attending.